Hello, and welcome to this video series on algorithms. This is part 7 of Module 4, where we focus on greedy algorithms. In this session, we continue our discussion by examining how greedy strategies can be applied to clustering problems. Clustering is the task of grouping similar objects together. It is an unsupervised learning technique, meaning there are no predefined labels, and clusters must be discovered directly from the data. The core goal of clustering is twofold: maximize similarity within each cluster and minimize similarity between different clusters. In other words, objects in the same cluster should be close according to a chosen distance measure, while objects in different clusters should be far apart. To achieve this, clustering algorithms rely on well-defined distance metrics, such as equidistance or other domain-specific measure tailored to the data. Clustering is widely used because it can automatically reveal patterns, groups, and unusual behaviors in data. In marketing, clustering supports customer segmentation. It helps business find groups of users with similar purchasing habits or interests. In natural language processing, it groups documents into topics without any manual labels. Clustering is also essential for anomaly detection, such as fraud detection or network intrusion monitoring. By modeling what normal data looks like, it can flag outliers as potential anomalies. In biology and medicine, clustering is used to analyze gene expression and other high-dimensional datasets. It helps identify functional groups, co-regulated genes, and evolutionarily related sequences. Overall, clustering is a versatile method for uncovering structure in unlabeled data. To understand clustering from an algorithmic perspective, we begin with its basic formulation. We are given a set of n objects, x equals x1 through xn, and a function d that measures distance or dissimilarity between every pair of objects, xi and xj. The goal is to partition these objects into clusters so that objects in the same cluster are close together, while those in different clusters are far apart. If an object can belong to exactly one cluster, then the clustering is called hard clustering, which is the primary focus of this video. On the other hand, if an object can belong to multiple clusters, we call such clustering soft clustering. Methods such as Gaussian mixture model produce soft clustering. There are many clustering algorithms, but in this video, we focus on hierarchical agglomerative clustering. Hierarchical clustering builds a tree, or dendrogram, that shows how all input objects are grouped at different similarity levels. The figure on the right illustrates this idea. Like k-means, if we specify a value k, the method can cut the dendrogram to produce k disjoint clusters. For this reason, hierarchical clustering is treated as a hard clustering method. Without specifying k, it simply generates the full dendrogram. One common way to perform hierarchical clustering is to start with each object as its own cluster, and then merge the closest clusters step by step until k clusters remain. This approach is called agglomerative clustering. In this video, we focus on how to perform hierarchical agglomerative clustering using greedy strategies. To perform agglomerative clustering, we need a way to measure how similar two clusters are. We call this measure the spacing between the clusters. One simple definition of spacing is the distance between the closest pair of objects in the two clusters. Formally, for clusters CA and CB, the spacing SCA-CB is the minimum distance between any object xi in CA and any object xj in CB. Because this method uses the single closest pair to represent cluster similarity, the resulting approach is called single-linkage clustering. Given a clustering, we can define its quality FC as the minimum spacing between all pairs of clusters. A larger minimum spacing means the clusters are more clearly separated. Thus, the goal of hierarchical agglomerative clustering under this definition is to maximize FC. Here is the pseudocode for the single-linkage clustering algorithm. The algorithm takes three inputs: X, the set of objects, D, or pairwise distances, and K, the target number of clusters. The idea is simple. We start with each point as its own cluster. At every step, we look at all pairwise distances and choose the smallest distance between 2 points or clusters that are not yet connected. When 2 points or clusters are merged, we treat the result as a single cluster for all future steps. Step 1 sorts all distances in ascending order. Step 2 initializes each object as an individual cluster. Step 3 repeatedly selects the smallest remaining distance and merges the corresponding clusters. The algorithm stops when exactly k clusters remain. This diagram shows how single-linkage clustering gradually merges individual objects into larger clusters. It is easy to see that single-linkage clustering is essentially the minimum spanning tree, or MST algorithm, with an early stopping rule. The only difference is the termination condition. Single-linkage clustering stops when k separate clusters remain. In contrast, the MST algorithm continues merging until all objects are connected into one tree. Recall that the single-linkage clustering algorithm claims to produce k disjoint clusters while maximizing FC, the minimum spacing among all pairs of clusters. To justify the claim, we first show that the algorithm correctly produces exactly k clusters. We start with n clusters, where each object is its own cluster. In each iteration, we merge two clusters. So, the total number of clusters decreases by 1. After n-k such merges, the number of clusters is reduced from n to k. Therefore, the algorithm indeed produces k clusters. Next, we show that the single-linkage algorithm thus maximizes the minimum spacing FC among all clusters. In other words, among all possible ways to form k clusters, the clustering produced by this algorithm has the largest possible minimum distance between any pair of distinct clusters. We begin by assuming that all pairwise distances are sorted in ascending order. Each dot in the diagram represents one of these distances. As the algorithm runs, some distances are selected, and their corresponding clusters are merged. We mark the selected distances in red. Other distances are examined but not selected because their objects are already in the same cluster. We mark these distances in yellow. Let the last distance chosen by the algorithm be d star. This is the distance used in the final merge before the algorithm reaches k clusters. Since d star was selected to merge two clusters, it must represent an in-cluster distance. Because all distances are sorted in ascending order, and d star is the last in-cluster distance chosen, every remaining between-cluster distance must be greater than or equal to d star. Therefore, the minimum spacing fc of the final clustering is at least d star. Now, suppose there is another clustering C prime that differs from the greedy clustering C. Because the two clusterings are different, they must disagree on at least one cluster. So, there must exist two objects, xi and xj, that are in the same cluster CR in C, but in different clusters C'S and C'T in C prime. This situation is illustrated in the figure on the slide. Since xi and xj are both in cluster CR, they lie in the same spanning tree. So, there must be a path in C that connects xi and xj. Because xi and xj belong to different clusters in C prime, at least one edge on that path must cross between clusters C'S and C'T. Let the endpoints of this crossing edge be x and x prime. Since x and x prime are both in cluster CR, their distance dxx prime is an in-cluster distance for the greedy clustering C. Therefore, it must have been selected at some point by the greedy single-linkage algorithm. Because the algorithm always selects shorter distances before longer ones, dxx prime must be no greater than d star, the last distance chosen. In other words, dxx prime is less than or equal to d star. Know that x and x prime belong to different clusters in C prime. So the distance dxx prime is a between-cluster spacing in C prime. Because fc prime is defined as the minimum spacing between any pair of clusters in C prime, we must have fc prime less than or equal to dxx prime. Combining this with the earlier result, dxx prime is less than or equal to d star, and the fact that d star is less than or equal to fc, we get fc prime less than or equal to dxx prime less than or equal to d star and less than or equal to fc. This shows that the minimum spacing fc prime is always less than or equal to fc. In other words, the greedy single-linkage clustering algorithm produces a clustering with maximum minimum spacing among all possible clusterings. Thus, single-linkage clustering indeed maximizes the minimum cluster spacing. Now, we analyze the time complexity of the single-linkage clustering algorithm. Let n be the number of objects. In step 1, sorting the objects require O n squared log n time, because there are n squared distances. In step 2, initializing each object as its own cluster takes O(n) time. Finally, step 3 processes each of the n-squared distances in sorted order. For each distance, we may need to merge the clusters containing xi and xj. Using a union fine data structure, each merge takes O log n time. As a result, step 3 also takes O(n) squared log n time. Combining all steps, the overall running time is O(n) squared log n. Its space complexity is O(n) squared, which is required to store the pairwise distance matrix. Besides single-linkage clustering, another way to measure the spacing between two clusters is average-linkage. Average-linkage clustering defines the spacing between two clusters as the average of all pairwise distances between the objects in those clusters. This approach considers every object in each cluster when measuring similarity. As a result, the spacing measure is more comprehensive and less biased toward individual close pairs. Unfortunately, changing the spacing definition also complicates the algorithm. In single-linkage clustering, the distance between two objects never changes as clusters are being merged. But in average-linkage clustering, the distance does change whenever clusters are merged. For example, suppose we have three clusters, Cx, Cy, and Cz, and we already know the average linkage spacing S Cx-Cz and S Cy-Cz. After we merge Cx and Cy into a new cluster Cxy, the spacing between Cxy and Cz becomes unknown. We must recompute this new distance from scratch because it depends on all pairwise distance between the objects in Cxy and objects in Cz. Because each cluster can contain up to O(n) objects, this computation takes O(n) squared time. In addition, we must recompute the spacing between Cxy and every other cluster. There can be up to O(n) such clusters. As a result, updating all spacings after each merge takes O(n) cubed time, which is significantly slower than the single-linkage algorithm. To avoid recomputing the exact spacing, we can use a heuristic to estimate it. After merging Cx and Cy into Cxy, we can approximate the new spacing to another cluster Cz as SCxyCz equals SCxCz plus SCyCz minus SCxCy divided by 2. Geometrically, this approximation behaves like measuring the distance between the centroid of Cxy and the centroid of Cz. With this heuristic, updating all spacings after each merge takes only O(n) time instead of O(n) cubed time. Because the spacing values change after every cluster merge, we must also modify the clustering algorithm. The main issue is that the order of spacings can change, so we can no longer rely on a fixed sorted list. To handle this, we store all spacing values in a heap, which allows fast retrieval of the current minimum spacing. The toy example on the slide illustrates this idea. On the left, we have 5 objects, A through E, each starting as its own cluster. In the middle is the pairwise distance matrix. On the right is a heap that contains all pairwise spacing values. The heap gives us the smallest spacing in O log n time and supports efficient updates as clusters are merged. First, we extract the smallest pairwise distance from the heap. This value tells us which two clusters should be merged next. In this example, the smallest spacing corresponds to objects A and B. So we merge their clusters. We now merge clusters A and B into a single cluster AB. Next, we update the heap. We remove all spacing values that involve clusters A or B, and we insert new spacing values for the merged cluster AB. The new spacings for AB are computed using the heuristic formula shown earlier. In the distance matrix, these updated values are shown in blue. Recall that removing or inserting an element in a heap takes O log m time, where m is the number of elements in the heap. Here, the heap stores all pairwise spacings, so m is in O(n square). Thus, each heap operation takes O log n square, or simply O log n time. We only need to update the spacing values involving clusters A, B, and AB. There are O(n) such updates. Therefore, updating the heap after this merge takes O(n log n time overall. Next, we again extract the smallest spacing from the heap. This gives us the next pair of clusters to merge. In this case, the smallest spacing corresponds to clusters D and E. So we merge them into a new cluster, DE. We then update the heap by removing the old spacings involving D and E and inserting the new spacings for the merged cluster DE. Next, we extract the smallest spacing from the heap and merge the corresponding clusters. In this step, the smallest spacing is between C and DE. So we merge them into a new cluster, CDE. And then, as before, we update the heap by removing the old spacings for C and DE and inserting the new spacings for the merged cluster CDE. Finally, we extract the next smallest spacing and merge the remaining clusters AB and CDE. The sequence of merges recorded during the process can then be used to reconstruct the dendrogram for the input objects A through E. Here is the pseudocode for the average linkage clustering algorithm. In step 1, we build a heap to store all initial spacing values. Because heap construction takes time linear in the number of elements, and we have O(n squared spacings, this step takes O(n squared time. In step 3, we iteratively merge clusters. The while loop runs at most n-1 times, since each merge reduces the number of clusters by 1. As discussed before, each merge requires updating all relevant spacings and maintaining the heap. This costs O(n log n time per iteration. Therefore, step 3 takes O(n squared log n time overall. Combining these steps, the average linkage clustering algorithm runs in O(n squared log n time and uses O(n squared space. In summary, We discussed hierarchical agglomerative clustering in this video. We covered two versions, single-linkage and average-linkage clustering. Both methods follow a greedy strategy and merge the most similar clusters at each step. Single-linkage offers a clean formulation and guarantees optimality under its spacing definition. However, its spacing measure is less practical because it depends only on the closest pair of objects. Average linkage provides a more meaningful spacing measure by considering all pairwise distances between clusters. But it requires heuristics to achieve a reasonable runtime and therefore does not guarantee optimality. Thank you for watching and see you next time.